Hi, NA Physics, it's Mr. Neff. Today let's talk about total internal reflection. But before we do, why couldn't the bicycle stand up on its own? I'll tell you at the end of the video. Now here's a simulator that I've used a few times in the past. It's from our friends over at University of Colorado, PhET. And it shows a laser beam coming down from air into water, and it shows it reflecting and some of it transmitting into the water and refracting. You can see that whenever that normal's on there, you can see this angle of incidence over here. You can see this angle of reflection. Those two are going to be the same. If I change the angle of incidence by 5 degrees, that changes the angle of reflection by 5 degrees. They're always going to be the same. You can see that the angle of refraction, that's this one over here from the normal over to the transmitted ray, that's not going to be the same. It's because there is refraction that is bending at the interface. And so this is smaller in this case. What we have here is instead of the light traveling along a straight line path and maybe going like along, maybe let me put it right here on 40 degrees, instead of it going here to 40 degrees, it has bent 11 degrees towards the normal. You always have that when every time you go from lesser index of refraction, this white substance is air, to a higher index of refraction, this blue substance is water, you're going to bend towards the normal. Now, if I change those around, if I change the air to water and the water to air, now you see that we have bending the other way. Angle of incidence, angle of reflection are still the same, enough about that. But now, rather than, here's my 40 degrees again, but instead of coming down here to 40 degrees and just going through undeviated, it's bent away from the normal, and it's bent away from the normal a good bit. Now, here's a neat thing. We always say that whenever incident light hits an interface, some of it reflects back into the first material and some of it transmits into the second material, except for whenever it doesn't. And here's why I say that. Now look, if I started at 30 degrees angle of incidence, I get 30 degrees angle of reflection, and I get 40 degrees angle of refraction. Now, as I go 5 degrees more on the angle of incidence, 5 degrees more on the angle of reflection, but now I've got a lot more on the angle of refraction. So the angle of refraction is growing faster than the angle of incidence is. And so you see something here. As I start heading down towards the interface, making this angle closer and closer to 90, this angle is going to beat it to the interface. This angle is going to be 90 way before this one because this one's growing really, really fast. And actually, once you start getting over here beyond 45, it grows extremely fast. And now look at what happened. Now, I don't see an angle of refraction at all. I did for a while, but now I don't. Is it just there but missing? Well, they give us this nifty light sensor, and we see 100% is incident, and in this case 20% is reflected and 80% is transmitted. But as I go forward, 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 now we see something. Now we see that 86% is reflected and only 14% is transmitted. Now watch something. As I get to just a little too big on the angle of incidence, now I have 100% incident and 100% reflected. And so it's not that I just can't see it down here, it's not down here. So this is a special case. Whenever you're going from a higher index to a lower index, the only time it's going to happen, I could have gone all the way down to 90 if I was going from air to water, but because I'm going the other way, because I'm going from a higher index to a lower index, now and in that case we're bent away from the normal, the angle of incidence, as it gets bigger, the angle of refraction will get bigger faster, and eventually it'll be up at 90 degrees. Once that happens, we say that that's the critical angle for these two substances. And if you have any more angle of incidence than that, you're going to get total internal reflection. And that's what we're seeing right here. So with total internal reflection, you're going to have that huge angle of incidence. And when you have that, because of it, you're going to have all of the energy reflecting back into the first material, not going on into the second material. So here, in this animation, you can see that as the as the angle of incidence gets bigger. Now this angle of incidence is on the bottom. They're showing an angle or light ray going from bottom to top. You can see here that the index of refraction for this bottom one is more than the one for the top one. And so as this gets bigger and bigger, you can see that the angle of refraction gets closer and closer to 90, and eventually it gets to 90. When it is at 90, that's whenever you have the critical angle. So it should be pretty easy for us to calculate then a formula for the critical angle. And so take a look at this. Here's a screenshot that I did from that other simulator. And so here is our first material. Let's say that that's N1 and it's big, and then N2 and that's small. Here's our angle of incidence, theta 1. And if you can remember from the simulator or even just from this animation that we just saw, when you get to the critical angle, you can see it right there. The reflected or the refracted ray is refracted along the surface like this, so that the angle of refraction is 90 degrees whenever you're at the critical angle of incidence. So looking at Snell's law, we can say that N1 sine of theta 1 equals N2 sine of theta 2. Now, whenever you're at the critical angle, we're going to call that theta 1 critical. N1 sine of theta 1 critical, that's equal to N2 times the sine of 90 degrees. And we know that sine of 90 degrees is going to be 1. So this is going to become N1 sine of theta 1 critical equals N2. And now how about I divide both sides by N1? Sine of theta 1 critical equals N2 over N1. And then I'll do an inverse sine of both sides, and I'll get theta 1 critical is equal to an inverse sine of N2 over N1. And that's a way for you to calculate that critical angle. And so if at the critical angle you'll have total internal reflection, and anything more than the critical angle you'll have total internal reflection. For you math types, you know that you have to take an inverse sine of something smaller than 1. And so, of course, N2 has to be smaller than N1. And so I kept making a point that you always had to go from a higher index to a lower index, and mathematically that makes a lot of sense here too. Now, a neat application of this, two neat applications of this. One is fiber optics. Fiber optics are a way to transmit information, but not through a copper wire, but through a thin strand of glass. So see what you do with fiber optics is you have this thin strand of glass that has a high index core and then a lower index coating on it. Now it's made out of glass, but it's not brittle. It's actually super nice and flexible. And so then whenever you send some light through that, see how every time the light hits the interface, the black curves, you see how the angle of incidence is always really big. You can see that pretty nicely up here on the still picture. See, every time it hits, here's the normal, and that angle of incidence is pretty large, just because of the geometry of being inside of that confined space. And so because of that, none of that light is going to get out of that optical fiber, but it's all going to reflect. And none of it ever gets out until you get over to the ends, and then whenever you get to the ends, then it can get out. And so there's a chance that you might even have something like this at your house. This is an audio cable that's fiber optic, and it's not as uncommon as you'd think. And so you're going to shine a laser light signal into the one end of this, and it's not going to be able to get out. It's going to totally internally reflect all the way down, and then it will get out whenever it's time to send out the signal. Another neat application of this is how the bottom of a diamond is cut. A diamond is a neat thing because the angle of incidence necessary to have total internal reflection actually isn't that high, because the index of refraction of that is pretty large. And so here we have diamond, which is going to have an index of refraction of something like 2.4, versus the air, of course, is going to have an index of refraction of 1. And so whenever that light comes down through the top and it hits the bottom, the way the bottom is cut, it's not going to be able to get out of there. It's going to bounce around inside of there for a while until finally it can reflect back up through the top. And that's what gives the diamonds their sparkly appearance. Okay, and did you hear why the bicycle couldn't stand up on its own? It was too tired.